Hi, you're listening to Ice World Podcast. I'm your host, Rob Taylor. I'm here with Josh Eveson today. Josh, welcome to the show.
Thanks very much. It's a pleasure to be here.
We're sitting in one of the modules at Halley Research Station on the Brunt Ice Shelf at approximately 76 degrees south. The modules here sit at about 22 metres above sea level, 30 kilometres or so from the edge of the continent itself. Josh, your work here is mostly studying the atmosphere and the weather, is that right?
That's right, yeah.
So talk us through a week of kind of what you do, what the order of things are, what equipment you're working with.
Okay, so a normal week for me involves a lot of observations. So we do what are called synoptic observations, which happen every 3 hours. So they start at 6 o'clock in the morning here and go on till 9 o'clock at night. And those are things like visibility, present weather, the amount and type of cloud, wind speed and direction, and the pressure.
So fairly obvious stuff, the kind of things that anyone can see and observe wherever they happen to be.
Yeah, standard kind of meteorological parameters.
And these synoptic observations, people are carrying these out all over, not just Antarctica, but also the globe.
Mm-hmm, absolutely, yeah. It's part of a global network that are used not only for sort of climate data, but also get fed into weather models. So used for forecasting. So
you get up early, you do your first synoptic observation. Mm-hmm. What other work do you do here?
So another thing which sort of Halley is quite famous for in particular is the Dobson ozone spectrophotometer, to give it its full name. So that's the instrument that measures stratospheric ozone and is the instrument that the ozone hole, which is one of the things Halley is most famous for, was discovered using back in sort of the early 80s, which led to sort of a seminal paper in 85. As to whether CFCs were linked to the ozone hole, they were, but only sort of theoretically.
And that's the work of kind of sort of the comparative planetologists it was in the end, wasn't it, that finally made that link?
I think it was, yeah. I can't remember their names, that's escaped me.
I don't remember the names either, but the work that they did was fascinating, really clever.
Yeah.
You take observations of the ozone and the state of the hole. Mm-hmm. And how is it? Is it growing smaller at the moment?
So this year is an interesting one in that it's the smallest ozone hole on record. So obviously the ozone hole has been on record since the 80s. And essentially it could be taken as a sign of recovery. However, there are some kind of unique atmospheric conditions that have been taking place this year. Unique's maybe a strong word, but
what are these conditions? What makes this year different?
Yeah, so this year there is a stratospheric warming event. So essentially, for the ozone hole to form, you need temperatures of around -70 for polar stratospheric clouds to form, and on these clouds are the interactions between the CFCs and the clouds that release chlorine. And chlorine is the element that sort of acts as a catalyst to destroy ozone. So if you get warmer temperatures, you get less of these clouds, you get less chlorine released into the atmosphere, and essentially you get a smaller ozone hole. So that's what's happened this year. And it's something that comes along every 20 years or so. So it's not necessarily indicative of long-term recovery.
So this is a noted cycle that happens every 20 years or so.
It's not exactly cyclical, but yeah, it's sort of fairly regular, and not entirely common.
A bit like an El Nino thing?
Yeah, exactly, that kind of thing, yeah.
Okay, so the Dobson spectrometer, I've seen it, and it's about, 1.5 meters long, a big old chunk of scientific equipment. It's quite some weight, and that fires straight up through a hole in the ceiling.
Yeah, so it's not exactly firing up, it's more receiving sunlight that is being fired down. So it's an optical instrument. You have a hole in the ceiling, as you rightly say, that takes in sunlight. And that sunlight obviously passes through the stratosphere where the ozone layer is. And from basically measuring two different wavelengths of UV light, one of which is strongly affected by ozone and one of which is not affected by ozone, you can measure the ratio of those and infer how much ozone there is above you. That's essentially the principle of how it works.
To explain to listeners why this is pertinent to anyone working in Antarctica, it seems surreal to wake up and have it maybe be -3 or 4 degrees on a cloudy day and put on sunscreen, but that's precisely what we have to do here. Otherwise, it's very, very easy to get quite bad skin damage while you're working down here, or on a sunny day to get incredibly badly burned very, very quickly. I know you launched the weather balloon. Is that part of the synoptics?
It's sort of connected. It's not part of the same system, but it's part of a global meteorological network. So yeah, every morning we launch a weather balloon, and that is, as I say, part of a global series of weather balloons that are all launched. And the idea is to get all the balloons at a certain level in the atmosphere, 100 hectopascals.
At the same time.
At the same time. Yeah, a sort of bizarre, sort of synchronized, but mass ascension of balloons into the atmosphere. So when is it? It's about 10 to 8 that we'll launch them here. And we're aiming to get them to 100 hectopascals at 12 midday GMT. And we're sort of 3 hours behind GMT here. So it takes about an hour and a half, 2 hours or so to get up to that level.
So you launched the balloons as well. What about the clean air sector? So tell us what the clean air sector is and what you're looking for there and what, if anything, you're finding.
Okay, so the clean air sector is to the south of the base. Basically, it's an area where we don't permit vehicles to go. People are allowed in. They don't emit too much carbon dioxide and other interesting chemicals. But yeah, vehicles are the main thing that we try and keep out. So the things that we're looking for are... So as well as looking in the stratosphere, we're also looking in the troposphere, which is the lowest level of the atmosphere, the level that we all live in and the weather happens in.
And that goes how high up?
It goes up to about 15 kilometres. It kind of varies depending on your latitude, but around that kind of level. So in the troposphere, ozone is a pollutant, which is sort of, you have to have a slightly counterintuitive way of thinking about it. It's good at a certain level in the stratosphere, but it's bad in the lower atmosphere. So ozone can be produced by what we call NOx, so nitrogen oxides, and they are produced in things like car engines. Right, so some of the things we measure are surface ozone to sort of assess how polluted the atmosphere is.
Okay.
So we're looking for tropospheric ozone. We're looking for other chemicals that can cause ozone depletion events, and so those are halogens, things like bromine and fluorine, and the sort of primary source of those is from sea salt. So we can look at that as well. What else have we got there? We've got a few sort of experiments from visiting scientists. So we've got some kind of filter sampling that are looking for biological cloud nuclei.
Biological cloud nuclei.
Yeah, that's a good sentence, isn't it?
Yeah, that's a beautiful phrase. And you'll have to explain to me what it means.
Okay, so...
It sounds like a baby cloud.
I mean, sort of. So clouds find it difficult to form without some sort of surface to form on. So imagine you're in your bathroom. You've just had a nice warm shower. What is there on the mirror?
Water is condensed.
The same kind of thing happens when you're trying to form clouds. Things like dust particles or bacteria, which is where biological cloud nuclei come into play. Sea salt is another one.
If it's biological cloud nuclei, are we talking about things like pollens?
Pollen, well, I mean, pollens you don't really get down here.
No.
But there are sort of bacteria and other things floating around in the air. So yeah, there's some cloud nuclei. Essentially, we've got air that is being sucked through a filter for a certain amount of time. Some of them, I mean, one of them is for the whole season. Another one gets changed every 50 hours or so. And what we do is we sort of package those filters up and send them back to their respective labs for analysis, where the people who've sent them now can look at them. Yeah,
that's quite cool. And how is that just running while you're here? Or
yes, so we don't run those through the winter.
So those will get sent back sometime in February,
and
they'll be analysed, and they'll presumably write up their findings.
Yeah.
Cool.
So yeah, in the clean air sector lab, which we shortened to the CAS lab, we're currently installing something that samples the air for greenhouse gases. So this is a collaboration with NOAA, and again they've got a kind of global network that they use, where they have these kind of glass flasks, and they have a pump that sort of pushes air into these glass flasks. They are pressurized and then sealed by hand normally, and then you send them back to NOAA, who sort of take their air samples from all over the world and produce data that shows how much CO2 in parts per million is there. So a few years back, I think it was the South Pole passed 400 parts per million, which is higher than it has been in the last 800,000 years, which we know from ice cores and things. So yeah, we sample the air, seal it in glass flasks, and send it back to the Americans, who sort of analyse the gases inside. I think they also analyse for methane as well. But what we're trying this season for the first time, because as we know, Halley is not wintering. There will be nobody here between February and sort of mid-November time. And so what we want is to have that record of gas sampled over the winter. So we're essentially automating this gas sampling process by having a sort of computer look at when was the last gas sample taken. Is the wind strong enough to take it? Because you want a nice, well-mixed atmosphere rather than a sort of stagnant one.
Yeah.
And then it goes, okay, conditions are right. I'm going to suck in a sample now. And through a hose, it sort of fills up these 2 flasks and then seals them for the rest of the winter.
That's quite cool.
Yeah.
And how many samples will it take over the winter, do you think?
So it's going to try and do 1 a week if conditions allow. So what's the maths on that? I think we're going to try and get about 32. So they come in these sort of big cases of about 16 each. So if we can fill 2 cases, we'll be delighted. It's the first time we've tried this, so anything we get is a win.
That's really cool.
Yeah. In terms of the thing that is checking whether conditions are right or not, will be in a heated box. So that's how we tend to run things in the CAS lab through the winter. We have them sort of containerized in a sort of 40 centimetre by 20 or 30 centimetre high box. And then, so that box can be heated much more easily than heating an entire room.
Yeah.
And so you can control the conditions inside that box much more easily than you can within an entire lab. And then you can run that through the winter. And it's much lower power than, say, heating an entire lab as well.
That makes sense, yeah. If there are no humans around, you don't need the lab to be nice and warm.
Yeah.
So have you any findings from what your observations have been down here, and any looking at the atmosphere or looking at the air that you've done?
So personally, I haven't had any findings. This is sort of fairly early on in my scientific career, and early on in my BAS career as well. I was down here for a short 3-month stint last year, and then I went sort of back to my old job at the Met Office before returning to BAS. So I've had a little spell away. And I think the nature of a lot of the work down here is kind of continued long-term monitoring.
It's these big data sets over a period of time in roughly the same place.
Exactly, yes.
That really is what the appeal of Halley is, isn't it, to researchers and scientists?
Yeah, I mean, it's got such a long history in terms of it's been going since the 50s. And, having a data set like that, whether it be in terms of stratospheric ozone, temperature and sort of meteorological records, the gas sampling and things are slightly newer, but we've still been doing that for a fairly long time, and the balloon launches as well have been going on for I think decades. So having that continuous data set from a set location, albeit the ice shelf moves a bit, so does the base occasionally, but allowing for that, you've got a really nice set of data, and that's why we're trying to automate things through the winter, because we're starting to get gaps in our data sets. And if you start getting that, then perhaps the appeal of Halley starts to weaken a little bit as this kind of data factory,
Yeah, the automation is something that obviously that Bass is really excited about, because once they've got the skills and the technology to do that here at Halley, which they're obviously very, very close to doing, they've had a lot of success already, there would be nothing to stop them from rolling that out elsewhere.
Mm-hmm.
So if you had it so that, you maybe need essentially a couple of porta cabins or containers worth of gear, and that's an automated system that can run and run and run, that becomes a very cost-effective way to get quite a lot of data in potentially loads of other sites as well.
Yeah, absolutely.
Which is quite cool to look at.
And sort of even in quite remote sites, this kind of microturbine technology that's powering a lot of the automation through the winter. It's fits in a shipping container, so that's one container. And if you have another container full of your scientific equipment, then that's 2 containers worth, and you can pull that along quite happily to I was going to say almost anywhere on the continent, but
pretty much anywhere.
Yeah, you can take it to a lot of places, a lot of very remote places.
It's an exciting thought, that.
Yeah.
Josh, thank you very much for coming on the show. It's been really interesting.
Okay, thank you, Rob. It's been a pleasure.
You've been listening to Ice World, the podcast on behalf of the British Antarctic Survey.